Hello and welcome to lecture 46. We are discussing design of low speed contra-rotating fan. In last session we have discussed about the design calculation for rotor 1 at the mid station, where we have assumed our total pressure rise expected to be 1200 Pascal. Then we have started doing calculation at say mid station, as well as we have done our calculation at the hub station. Now say this is what we have expected. Here in this case we are expecting our total pressure rise at the hub to be say 500 Pascal, for what we have done the calculation at the hub station. Today we will be moving with say design at the tip station, where we are expecting our total pressure rise to be 1900 Pascal. So let's move it. So this is what we can say our condition. We have our entry to be axial entry. So that's the reason why my alpha 1 at the tip, that's what I say 0. My CW1 at the tip, that also will be 0. We can say our peripheral speed, now this is what will be based on my tip diameter. So it is coming 50.89 meter per second. Once we know what is our peripheral speed and we already know our axial velocity, that's what we are assuming to be constant. So that's what will be giving me my relative blade angle at the entry beta 1 as say 48.90. Now in line to what all we have done, we will be doing our calculation based on our fundamental understanding of thermodynamic and aerodynamic work. So here at this station we are expecting our total pressure rise to be say 1900 Pascal, and that's the reason if you look at, we are calculating our say pressure at the outlet near the tip, that's what is say it is coming say 1.0322 kilopascal. Okay, we are calculating our pressure ratio, that's what is coming 1.011. Okay. Now once we know what is our delta P0, we can do our calculation for say delta T0 for rotor 1 at the tip, and that's what is coming 1.87 Kelvin. Now once this is what is known to us, based on our fundamentals, we can say we are comparing our aerodynamic and thermodynamic work at that station to be same, and based on that we are calculating our beta 2, that's what is coming say 16.53. Now once beta 2 at the tip is known to us, we can calculate what will be my delta beta, and this delta beta at the tip, it is coming 32.37 degree. We can calculate our specific energy for say tip station. Okay, that's what is coming 1.88 kilojoule per kg. Now in order to do the calculation at say tip station, we need to have our CW2 at the tip to be known to us. So what we know from my 10 law, it says 10 beta 2, it's nothing but U minus CW2 divided by CA. Now be careful what all we are putting, that's what is at the tip station, because we are doing our calculation at the tip station. That's what is giving me my work component to be say 37.72. Okay, so if you look at here, my velocity triangle, that's what has changed accordingly. So be careful about that part. Once this is what is known to us, we can do our calculation for alpha 2, because that's what is my requirement for downstream rotor. So it says my alpha 2, it is coming say 40.35 degree. Now once these angles are known to us, we can do calculation for what all will be my relative velocities. So my relative velocity at say entry, it is coming 67.54 meter per second. At the outlet it is coming 46.31, and if we are calculating our de-Holler's factor, that's what is coming 0.69. So you can say we are having variation of our de-Holler's factor at hub, mid and tip station. Okay, when we will see the comparison, that will make more sense. Now we need to calculate what will be our diffusion factor at the tip station. So we will be calculating our pitch, we will be calculating our solidity. So pitch we are calculating based on pi d by say z. Here my number of blades we are assuming to be 19. So that's what is giving me my pitch to be 0.067 meter, and if we are putting our chord to be 0.045, that's what is giving me say my solidity as 0.67. Okay. Now my diffusion factor at the tip, if we are calculating, that's what is coming 0.73. Okay. And my power calculation, if we compare at the hub, at mid station, at the tip, this is what is tip loaded rotor, and that's the reason if you are calculating your power at that station, this is what is coming 17.71 kilowatt. Now based on Carter's rule, we can do our calculation for say M factor, and this is what is coming 0.38. Okay. Now say as we have discussed for say selection of our incidence angle, so we are assuming our incidence angle at the tip to be -2 degree. What all are the reasons? What we have discussed earlier. Again, in order to take care of your change of incidence, by default designers they are adding that angle, so that when the blade, that's what will be acting under off design condition, still behave like working in a design condition. Okay. So conventionally we are assuming this to be say -2 degree. If we are putting that, it says my camber angle, that's what is coming 63.64 degree. My deviation angle, it is coming 29.26 degree, and my stagger angle, that's what is coming 19.08 degree. Okay. Now we can understand we have our calculation at mid station, we have calculation at hub station, we have calculation at say tip station. So all the required parameter for the design, that's what we have done calculation. So let's see, this is what will be coming in sense of our design sheet at hub station, mid station, and say tip station. So if you try to compare, so if you look at my de-Holler's factor, that's what is coming to be 1.07, that's what is at the hub, and 0.7 near the tip region. If we are considering our diffusion factor, it is coming 0.15, and near tip, that's what is coming 0.67. Okay. Now if you are considering this as your case, it says my camber angle, that's what is coming 17.94 and 54.08. Let me tell you what exactly is the purpose here. So you know, this is what is our final design sheet. Okay. What we have assumed? We have assumed at hub our total pressure rise expected, that's what is say 500 in cents. Okay. So here if you look at, this is what is giving me 500, 1200 and 1900. Now in order to showcase what iterations we have done, say initially we have assumed at hub my total pressure rise as 700, at mid station we have not done any change, but at the tip, that's what it says 1700 Pascal. When we are doing this kind of calculation, just look at what de-Holler's factor we are getting, that's what is say 1.07. That's what is on higher side. But at the same time, if you compare my delta beta at the hub, that's what is coming 50.20. That's what is too large. Okay. Same way, if at the tip, if you are looking at, that's what is say 27.81. So you can say the blade what I will be making, that's what will be highly twisted blade. Okay. So what it indicates, now you need to play with your parameters. So what all parameters we need to play with. So here if you look at, say for this case, for our design what we have done at hub, we have taken our total pressure rise as a 500 Pascal, and that's what is giving me my delta beta as 37.18. You can compare these numbers. Okay. At the same time, near the tip region also, this is what is slightly on higher side, but you can say that's what is giving me my angle as say 32.37 delta beta. So by this way, you are having the flexibility to modify these numbers. And basically, you do initial calculation at the mid station with your pen and paper, verify that part, is it coming as the same number, then you make or extend your Excel sheet for hub and tip station. This is what is the advisable thing, and that's what will be giving me two extremes. At hub, what need to be my number, at tip, what need to be my number. Okay. Now here if you compare, say compared to my earlier assumption, diffusion factor, that's what is coming 0.18, and here this is what is coming 0.73. It is on higher side. Okay. We will discuss about this point, what is the reason why we are expecting this to be on higher side. Remember one thing, what all numbers, that's what is given in open literature, what all people they are discussing, that's what is applicable for stage, rotor and stator combination. That may or may not be straightway applicable for, say, the design case for contra-rotating concept. Okay, it is designer's choice, you need to play with the numbers. Okay. Now here in this case, if you are comparing, I am improving my de-Holler's factor in a proper way. At the same time, the camber angle that has reduced from say 51 at the hub to 63 at the tip region. Okay. Now once we have finalized with the two extremes and mid station, what we will be doing? We will be making the number of stations. Remember one thing, this blade, that's what is having aspect ratio of 3, that means my height of the blade will be taller or it will be larger compared to aspect ratio 1. It means I will be having blade height to be large. If that's what is your case, it is advisable to go with more number of stations. With the space as a constraint for this slide, so we have considered only 11 stations, but you can play with say 20 station, 21 station, even you can go with 40 station, nobody will stop you. Okay. So here if you look at, this is what is my distribution of delta P0. Okay. Now this delta P0, that's what is not been selected randomly. Remember one thing, there is no systematic rule you need to apply here. Many times students, they used to put, say, they will set this number in such a way that it will give the linear kind of trend or linear variation of total pressure. There is nothing wrong doing that part, but that's what is a mechanical kind of work. We are more towards say aerodynamic design, so you need to think in an innovative way, and that's how you need to keep on eye with the variation of delta beta. So just look at, when we are doing this, we are putting these numbers, I will be having particular trend for delta beta. At the same time, just keep on eye for say de-Holler's factor. Okay. Same way you just keep on eye for what is happening with your camber angle. Just look at, this is what is showing me say particular trend for say my camber angle variation. Okay. Now once whole data sheet, that's what is ready with us, then you will say, sir, we will go with say now making of the blade. Now if you recall, I was talking to you say what Carter has given in sense of calculation for deviation angle, that's what is not giving the exact features what we are looking for. So these days people, they are comfortable with using the computational tool. So based on what all calculation initially we have done in last data sheet, that's what will be the input in sense of my camber and stagger angle. Okay. Once we are putting this camber angle and stagger angle, we will be observing what is happening near my trailing edge, and that's what will be giving you clue to modify your deviation angle. So in one of my paper, I have discussed how do we decide with this deviation angle. If you are interested, you can go through, you refer that paper, that will give you idea how we need to check with and why we need to change this angle. Okay. So based on CFD analysis, based on experiments, or based on say experience, you can modify your deviation angle. So once you are modifying your deviation angle, you need to take some number. So this is what is my assumed number. once we are doing this delta calculation, accordingly my camber angle I need to correct, because my earlier deviation angle it was different. Now I need to put corrected camber angle. So this is what is my corrected camber angle. Be careful about this. Same way, when my camber, that's what has been changed, I need to do modification for say stagger angle. So it says my corrected stagger angle, that's what is say beta minus incidence and theta corrected by 2. Okay. Now this corrected camber and corrected stagger, these are the angles which we need to use for making of our blade. Be careful about this part. Okay. It may be possible, say like deviation angle what you are assuming, that may be coming different at different stations. You can say you will be assuming your deviation angle more near the hub region. You may be reducing your deviation angle to moving towards a tip region, but that need to be in a systematic way. Okay, and that's what the computational tool, that's what will be coming into the picture. That's what will give you how do we move forward with. Now for this case, say we have assumed this to be say 4 degree, and if you do it say at mid station, we have done calculation for corrected deviation, corrected camber and corrected incidence, okay, or corrected our stagger angle. Okay. So you can say by corrected deviation, corrected camber and corrected stagger we have done calculation. Now this logic, if you look at, this is what is my assumed deviation angle. As I told, what you need to do is maybe you can plot your velocity contours, you can plot your CP distribution at particular station, then you just observe how my flow is behaving on my suction surface, on my pressure surface, how it is behaving near the leading edge, how it is behaving near the trailing edge, and based on that systematically you need to assume this number. So for this design we have assumed this to be 4 degree, and that's what will be giving me my corrected camber and corrected stagger angle. Okay. Now once we are achieving this corrected camber and corrected stagger angle, we can say we have our equation for say C4 profile. In that C4 profile, do not forget what angle we were considering theta, now that angle need to be corrected angle. Okay. Do not miss this part. So purposefully this slide has been kept intentionally here. Okay. Now same way, what stagger angle we have considered for our earlier program, now that input will be corrected stagger angle. So accordingly we will be getting our blade geometry. Okay. So for rotor 1, this is what we say in sense of we are doing calculation for say this corrected camber angle and corrected stagger angle. Let me show you say how we will be having our variation of beta 1 and beta 2. So you can say this is what is my delta beta variation, this is what is representing my delta alpha variation, and delta beta, that's what is varying in a different way here. My diffusion factor at the hub, it is coming to be lower, and my diffusion factor at the tip, that's what is larger, that's what is reflecting in sense of our de Holler's factor also. Okay. Now when we are putting all our angle calculation for different 11 stations, so if you look at, this is what is representing my 1200 and 800 Pascal distribution. So this is what is the geometry for my rotor 1. Okay. So here if you look at, say this is what is my hub curvature, my mid station and my tip station. Okay. So same way here, this is what is my hub and tip. Since this is what is a rotating component, we will be taking all our aerofoils about CG. Now let me show you here. So this is what is we have done our initial calculation with, that's what is with 1100 and 900 Pascal. So you can compare the change of the shape for my blade. Just look at, this is what is my rotor 1, this is what is my rotor 2, and if you are looking at how my angles, that's what is changing. Now be careful what all we are discussing. That's what delta P0 you are distributing along the span. It may be having some variation. So many times, say initial design, people they are doing with axial seat, then they realize they are looking for say particular kind of performance. That's what they may or may not be achieving. Then at that time, say span wise they will be doing their calculation for total pressure rise, and based on that comparison, according to the expectation, my delta P0, that's what can be changed. When I am changing delta P0, accordingly I need to make my distribution in a smooth way. If you look at here, say my variation of beta 1 and variation of beta 2, that need to be smooth, it should not be zigzag. Otherwise it will not permit you to make the blade. And that's the reason, as I told, you take more number of stations. Say here we have taken 11 station, you go with say 22 station, 21 station. No one will stop you. Okay, and this is what now when we are comparing, this is what is a comparison for router 1 for two different loadings. So here if you look at this golden color, what you are observing, that's what is say 1200 and 800 Pascal. That means my expected total pressure from router 1 is 1200 Pascal, and my router 2, that's what is we will be calculating immediately. So here if you look at, this is how my angle variations, that's what is coming into the picture. So if you look carefully from leading edge, okay, so from hub to tip, I will be having the variation of angle. At the same time, towards the trailing edge also, I will be having highly twisted blade for 1200 Pascal. Okay, so remember at all station, my distribution of pressure, that's what is different for both the blades. This is what is for representation purpose. Okay, now you can understand if you try to look at what is happening here near the tip region, I am having my angle, that's what is coming to be larger. Okay, now that's what if you go through your aerodynamics, it says when I'll be having my blade to be highly cambered blade or slightly more cambered blade, I may be having chances for my flow to get separated. So aggressively if you are doing design, many times maybe as per your blade shape or as per your computational study, you may need to modify these angles or you may need to reduce your loading. Sometimes you fail, maybe you need to go with the higher loading. So this is what is all designer's choice. Okay, so I'm sure this is what it is giving you idea about the design for router 1. So here we are stopping with, in next lecture we will be discussing about the design of router 2. Okay, so be with me and we will be discussing design of router 2 based on fundamental concept, and later on we will be comparing both the routers by using two different loadings. Thank you.